This video explains how to solve a thermochemistry problem from General Chemistry 1215. The problem today is a 100 milliliter sample of a 1 molar NaOH solution is mixed with 50 milliliters of a 1 molar H2SO4 solution in a large styrofoam coffee cup. The cup is fitted with a lid through which a calibrated thermometer passes. The temperature of each solution before mixing is 22.3 degrees Celsius. After the NaOH solution is added to the coffee cup and the mixed solutions are stirred with the thermometer, the maximum temperature measured is 31.4 degrees Celsius. Assume that the density of the mixed solutions is 1 gram per milliliter. The specific heat of the mixed solutions is 4.18 joule per gram times degrees Celsius, and no heat is lost to the surroundings. First, we'll need to write a balanced chemical equation for the reaction that takes place in the styrofoam cup. Then we need to answer the question, is any NaOH or H2SO4 left in the styrofoam cup when the reaction is over? We need to calculate the enthalpy change per mole of H2SO4 in the reaction. For part A, I will go quickly through writing a balanced chemical equation. Hopefully, at this point in the semester, you already have this down. If not, I hope any insight I provide is useful to you. First, you need to write out all the reactants and products. The reactants for this problem are given in the question, NaOH and H2SO4. Then, the rest of them have to be deduced from the fact that NaOH and H2SO4 are a base and an acid, respectively. So, we'll have NaOH aqueous plus H2SO4 aqueous is equal to H2O liquid plus Na2SO4 aqueous. The way I know this is because OH is a base and H2SO4 is an acid. When we're adding these, we'll create a water and a salt. So, we create the H2O from the OH and the H2, and then from the Na and the SO4, we'll create Na2SO4, just making that a balanced molecule and calling it good. Then we need to make sure that there are the same number of all atoms on both sides. In example, there are currently 2 Na atoms on the product side and only 1 on the reactant side. So you'll need to put a coefficient of 2 in front of NaOH to balance that part of the reaction. From there, it's relatively simple. You just check and see there are the same number of Na on both sides. You need to put a 2 in front of the H2O in order to balance the numbers of O's with the number of H's. There only needs to be 1 SO4 and then your reaction is balanced. So our final product here is going to be 2 NaOH aqueous plus H2SO4 aqueous equals 2 H2O liquid plus Na2SO4 aqueous. Now we need to check to see if this is a limiting reagent problem. You can tell that this is what the problem asks for because it is asking if any of the reactants are left at the end of the reaction. I checked to see if there is any of a reactant left over by looking at the moles present at the beginning of the problem for each molecule and their ratios to each other. First, calculate the moles of NaOH. 0.1 liters, which is equal to 100 milliliters, times 1 mole per liter, which is equal to 1 molar, equals 0.1 moles of NaOH. The liters cancel out and you're left with just moles. Then we'll do the same calculation for H2SO4. 0.05 liters, which is equal to the 50 milliliters from the question, times 1 mole per 1 liter, once again, 1 molar, is equal to 0.05 moles of H2SO4. This has 2 times as much NaOH as H2SO4, which is the same as the ratio from the balanced equation. So there should be no NaOH or H2SO4 left in the cup. 0.1 moles of NaOH over 0.05 moles of H2SO4 is equal to 2 moles of NaOH to 1 mole of H2SO4. This is just restating the same ratio that we created in part A of the problem by balancing the equation. Now on to part C, solving for change in enthalpy per mole. So for this part, we start with 2 equations. Change in enthalpy of reaction is equal to negative change in enthalpy of surroundings, and change in enthalpy of surroundings is equal to, for this problem at least, the mass times the specific heat times the change in temperature. This will be true of all of the equations equations that you need for reactions at constant pressure in coffee cup calorimetry. You will need to use different equations for bomb calorimetry, which is done in a closed system, but at variable pressure. So, change in enthalpy of reaction is equal to negative mass times specific heat times change in temperature. For this problem, mass is equal to the 150 total milliliters that you can get from adding the two startings of the reactants from the question times the 1 gram per milliliter density given to us in the question equals 150 grams as the mass. Then specific heat was given in the problem as 4.184 joules over grams times degrees Celsius. And delta T we can find from 31.4 degrees Celsius, the final temperature given in the problem, minus 22.3 degrees Celsius, the initial temperature given in the problem. This is equal to 9.1 degrees Celsius as our change in temperature. Now we just need to plug these numbers into our equation to get change in enthalpy of reaction is equal to negative 150 grams times 4.18 joules over grams times degrees Celsius times 9.1 degrees Celsius is equal to negative 5,705.7 joules, which is equal to negative 5.7057 kilojoules. We know from the previous step that there are 0.05 moles of H2SO4 reacted, so the change in enthalpy per mole of H2SO4 can be expressed as delta H reaction per mole, or negative 5.7057 kilojoules over 0.05 mole of H2SO4, which equals negative 114.114 kilojoules per mole of H2SO4. Accounting for significant figures, which is 2 due to the molarity of 1.0 molar. See, there's only 2 significant figures there. Additionally, you can see the same 2 significant figures from our calculated change in temperature. When we're doing subtraction, we keep to the largest decimal place that is in both, in this case the tenths place in both of them, which for this problem leaves us with 2 significant figures for change in temperature. Then using our 2 significant figures, we restate the change in enthalpy per mole as negative 1.1 times 10 squared kilojoules produced per mole of H2SO4 reacted. Thank you, and good luck with your studies.